Okay, now briefly, if we get 0 heads 9 times, 1 head 41 times, 2 heads 62, 3 heads 47, 4 heads 11 times, how many heads did we get, right? Well, people want to just, some people just want to add the number of heads. Well, 1, 2, 3, 4, add up to 10, so we got 10 heads, right? And some people might want to add up these numbers. Well, if you add up these numbers, you do want to do that, but that doesn't give you the number of heads. That gives you how many flips there were, right? So now if you want to get the total number of heads, well, you got this 9 times. Well, you could write down 9 zeros, okay? And you got 1 41 times. You could write down 41 ones. I don't have room. It goes down approximately to the floor. 62 twos probably goes down through the floor. But and 37 threes go pretty low. And 11 fours, I actually wrote down 11 fours. So you could write a long column of 160 numbers and add them up, right? That would tell you how many heads you got on all those flips. But it's obvious, and most of you knew immediately what it was. It's obvious there's a shortcut to that, because if you add up 62 twos, you're going to get 126 heads, right? In 62 twos, there were 106. Yeah, 62 times you got 2 heads, you got 126 heads. Okay, 37 times you got 3 heads, that's 111 heads. Just multiply. So, you could put that in an array. Now we could multiply those numbers out. Okay, you could even indicate, call this F, which is the frequency with which you got that many heads. Call this X, which is your number of heads on given flips. So you multiply your X's by F's and you get these numbers, but you don't need to have this rule, multiply X by F, because it's common sense to multiply this by this, right? So I think you don't start with a formula. I think you start with common sense, because if you do this, people are going to naturally shortcut it. Unless you have a bunch of people in your class who just don't want to think, so they don't, and they never learned. And then you got to use a formula and deconstruct that for those people, okay? So whether you start with the formula or start with common sense, I go with common sense, but then be able to put it in symbols. So putting that process in symbols, I got X times F, and then I add those up, and that, we'll call that the sum of the X times F, right? You add up all your X times F's, and that gives you your total number of heads, which is 320, right? That's a total number of heads on 160 flips, so what's the average number of heads? The mean average is what you call, you use X bar for that, that's pretty standard notation. That's the mean, and that's the total you get, total number of heads, over the number of flips, right? And that's 320 over 160, it's 2. And just looking at these numbers, you know it's going to be kind of close to 2, right? And if you did the histogram, the histogram would have 62 up here. You would have 41 here, and 37 here, and 9 here, and 11 here. I didn't draw that very well. But again, to reinforce where we are, that could be well modeled by a bell-shaped curve. Okay? Now, does that halfway make sense? Probably more than halfway. Okay, so you get the mean. Now, there's this other thing you want to calculate. You want to see, okay, well, your mean is here. Now, these things deviate from the mean, right? In other words, 1 deviates from the mean by 1 unit, right? 2 deviates from the mean by 2 units. And of course, 3 deviates from the mean by 1 unit, 4 deviates by 2, right? So a deviation, well, the deviations here the deviation from mean is 1 for this histogram. And deviation of this one from the mean is 2. Okay? So, we can continue the table now that I've interrupted it with this picture, but we'll continue over here. You can calculate the deviations, that's easy. The deviation of every one of these 9 is 2. Deviation of every 1 is 1. Deviation of 2 from itself is 0. Deviation of 3 is 1. The deviation of 4 is 2. We understand? But these are the deviations that go with these rows. Okay? Now, how do we get the mean of our deviations?
You add them up and you divide by 5.
Okay, well, what do you add? Do you add these numbers? Divide by 5? No, because there are only 9 of these. There are 41 of these. There are 62 of these. Of course, they don't deviate. There are 41 of these, and there are 11 of these, right?
You divide 320 by 5.
So you're going to have 9 times 2. You're going to have 41 times 1. You're going to have 37 times 3. You're going to have 11 times 4. Okay? In other words, it's obvious that you got to do that if you're going to calculate the deviation of every one, because every one of these has a deviation. Every one that you list, if you make the big long list, deviates by 1 or 2 from the mean in this case. So this is, you could call that frequency times deviation, because now you understand why it's okay to kind of annotate it, and you have then your total deviation. Now I'm going to do this in my head. That's 18, 18 and 41 is 59. That's 111. That gets you up to 170. And 44 gives you 214. So maybe I got 214. Hang on before I lose my numbers. Yes?
Why are you multiplying 47 by 3 when it only deviates by 1?
Well, that was ridiculous, wasn't it? Okay? I started writing down numbers without thinking about what I was writing down. So obviously it's not 214, everybody knows that. 37 times 1, 11 times 2. Let's see, I was up to 59 here. 59 and 37 is 96, and 22 is 118. Maybe. You know, y'all can figure that out, but let's pretend I'm right. Okay? So the mean deviation is 118 over 120, which is like 0.98 approximately. A little less than 1. Okay? Make sense? Okay.
Why are you dividing 118 by 120?
As I say, your mean deviation is 118 divided by 160, which is 0.7. I think that'll come out around 0.74. Between 0.73 and 74.
Where do you get the 160? Is it from the
The amount
total
of
number of
flips.
flips?
Yes.
No, actually, it's 0.74. Okay, that's a little over 0.7, like 0.743 or something. Okay? Now, does that process make sense?
So you have all your things, and then
You
make
what?
you make your deviation. So your 0 number of heads is going to be deviation of 2. 1 number of heads is going to be deviation of 1. 2 number of heads is going to be deviation of 0. 3 number of heads is going to be deviation of 1. 4 number of heads is going to be deviation of 2. So you're going to multiply all your numbers except for the 0 deviation, like you normally did, like you did in the first.
Well, you're going to multiply that too, so we can do 62
times
times 0. I didn't write it down because it came out 0. It's probably best if I include it in the, okay?
And then you add all of those up and you get your total deviation, and you divide your total deviation by the number of flips to get your mean deviation.
Yep. That should make sense, especially if you think about it again, as you will, if you,
So 0.74 would be the relative amount of deviation around the whole bell graph.
it tells you about how far things are spread out.
All right. I got that. We. Again?
Measure the spread of the distribution, where this is a picture of the distribution, right? Or at least a picture representing the distribution. Not a totally accurate picture because I just sketched it, okay? Now that's not, turns out not to be a real important quantity, but it's easy to calculate, okay? So now I'm going to tell you the important quantity, which is the standard deviation. And I think most of you calculated standard deviations probably by a formula without understanding how it, without starting from understanding how it represents a distribution, okay? But maybe you started with a formula and worked back to what it means, and that's okay too. Some people prefer to do that, and maybe they're right. It's not the way I like to approach things. I think a majority of students do better the other way, at least the majority of students who can profit from the course. Okay? Maybe the majority of students in the course will at least learn a little bit by the other approach. And I'm not to dictate just how that's done. I'm just telling you there are two different ways to do it. Each has its upside, each has its downside. But the downside is bigger for the smart people and the hard-working people, okay? The people who can really profit from the course. There are a lot of smart people who could profit from the course if they do the work and don't. You don't have to be a genius to understand this and profit from it. Okay, so most students could, but most students won't. So what do you do about that? I'm glad other people are making that decision. Could be a hard decision. Okay, but for you guys, this is the way I'm approaching it because I think this is the way you profit. Okay, now, your standard deviation is
Your CD is.
It's the square root of the mean of the squared deviations. Okay? So given the quantities that we have on the board, what's the first thing you would do to begin constructing the standard deviation? What's the first calculation that you would have to do?
Mean.
No,
You square up the deviations?
no. To do the mean, you have to have the mean of something, right? You have the mean of what? If you start by calculating the mean, what is it you don't have to calculate the mean of at this point?
Data points.
The what?
The data.
Oh, we've got those. We're not doing the mean of data points. What's it say to do the mean of?
Square root of deviations.
It doesn't say to do the mean of the square root of anything. It says do the square root of the mean of something.
Squared deviations.
Okay, so what do you do the mean of?
Take the mean of the squared deviations.
What do you need to do before you can take the mean of the squared deviations?
Square your deviations.
You better square your deviations, right?
2
Okay.
squared, 1 squared, 0 squared,
In
1
other words,
squared,
when
2
you read
squared.
this process, you don't start with the square root because you don't know what the mean is, and you don't start with the mean because you don't know what the heck the squared deviations are, right? You start by squaring your deviations. Does that make sense? Okay? And you need to know how to read a statement like that because you're going to experience them, okay? Also, if you're at the level where you can read that statement, you mean you're thinking at a little higher level, okay?
So
It's kind of like a nesting of parentheses, okay? You do the square root of quantity, mean of quantity, squared deviations, right? And we can write it down as a formula, which is the way it's usually done, so you never understand the words, okay? So you never understand what it really is, it's just something you calculate from a formula. Okay? Okay.
what does
And
that
this is
mean?
one of the most important quantities, maybe probably the most important quantity in statistics.
What is it going to
Statistics is
be?
extraordinarily important, yeah.
What are the numbers we're going to put in it? Is it going to be 118 square root of 118 squared?
I don't care about that, I want to know what the square deviations are, and then we'll answer your question.
So
One
are
step at a
we going to
time.
be squaring 2, 1, 0, 1, and 2, or?
Well, you're going to be squaring deviations, right? And what are deviations? Just what you said.
1, 0,
So
1,
yes, that's
2.
what we're going to be doing, right? Answer to your question is yes. The reason is, those are the deviations, okay? Right? So when you see mean of squared deviations, you don't start with the word mean, you start with squared deviations, which you don't have up there, but which we will have very quickly, right? So we squared the deviations. Okay? Now, how do we do the mean of the squared deviations? Well, you might think, well, we add up these numbers and find the mean, right? But no, because each of these numbers occurs a different number of times. And we're doing the mean of all the dang flips, not the mean of whatever numbers happen to be in the column that tells you what the deviation is for this number or that number.
Excuse me.
It's for every flip. And you're used to that. You probably would have done that anyway, but I want to emphasize it because often people will just do the most simplistic thing without thinking about their context. The context is you got 160 numbers here, and it's a mean of the squared deviations of all those results. So we could say it's implicit, so we don't write it. For this stay, we'll say in parentheses at least of all 160 flips, right? Okay? So what do we have to do with these? We've got to multiply each of these by how many times it occurs, right? So, you know, we'll write F times deviation, and we're going to get okay? And these, all three of these are exactly the same as they would be for the mean deviation, right? But the mean squared deviation, we've got to multiply by the squared deviation, so these two numbers here are going to multiply by 4. Now there aren't that many of them, so they're not going to have that big of an effect on your final result, but they will have an effect, and the fact that you're doing a square root of a sum has its effect. So what are you going to get? You're going to get 18, 22, you're going to get 40 more than you got here, so total of your square deviations is 158. So the mean, well, what's the next thing we want to do?
Get the mean.
So we've got the square deviations, And we actually added up the squared deviations without saying why. Why would we even think of adding up the squared deviations? What in this statement
Deviation.
motivated me, drove me toward adding up the squared deviations?
The square root of mean of squared deviation.
Okay,
So you have to
ignore
first get
square
the
root,
mean of the
we're
squared
just looking at
deviation.
mean of the squared deviations. How do you get the mean of the squared deviations?
Add them all up.
You add them all up. That's why I added them all up, right? So I'm working on the mean of the squared deviations. I should have kind of mentioned that before I added them up, but there it is.
Shouldn't
Okay?
you take the square root of that, of 158?
No,
No, you don't have
It
no,
says-
because 158, what is 158?
It's all of them added up.
It's the total of the squared deviations. That's not the mean of the squared deviations.
Okay, the mean is that over 160.
Yeah, exactly, and of course you know
And
that.
then take the square root of that,
Yeah.
correct?
Okay, so, it helps if you identify this as the total deviation squared, so you don't make the mistake of thinking that's your mean deviation squared, right? Okay? So you want to identify what you have at every step so that in the booming, buzzing confusion of this scheme, which is not very confusing after you've done it a couple of times, but for any scheme, you know, you're trying to work out some other scheme, follow some other algorithm, do some other thing. You want to identify what you have at every step to make sure you're doing the correct stuff. So the mean is 158 over 160, okay? Which is pretty close to 0.99. So what's the standard deviation? Well, not now. It's the square root of the mean of the squared deviations, right? So, when a number is real close to 1, its square root is twice as close to 1. And its square is twice as far from 1. That's something you can prove just using Algebra 1. And if I had more time, I'd show you, because I usually like to do that when it comes up if we don't have time. Okay? So it's kind of worth remembering, because it's an approximation that gets used a lot in like a physics course or chemistry course or whatever, where you're taking square roots of numbers close to 1. Or manipulate things, we can do that. Okay, so there's our standard deviation. Now you know how to calculate standard deviations, right? Okay, now let me tell you how this relates to the normal curve, that bell-shaped curve. I gave you n of x, the formula for the normal curve for variable x. But I had that mu and that sigma and stuff in there, okay? So a simpler formula for the same thing, and the way we're going to end up using it here
That's your formula for what we just did.
no, that's a formula for the normal curve.
That was part of last night's assignment.
So are we moving off?
Did I
of what
give
we
you
just
that?
did?
You gave us nz equals 1 over 2 squared pi e to the negative 1z
Negative
to the
z
2
squared.
squared, 2 divided by 2.
Yeah. That's a formula I should have given you if I gave you a different one I screwed up, but I think don't think
Are we moving off of what we were just doing?
Huh?
Are we moving off of what we were just?
No,
doing?
we're interpreting what we just did in terms of the normal curve. Okay?
All right, buddy.
So we're gonna plot this. Okay? So we're gonna plot this using our standard values. Of course, these are now z values. And here's n of z. Now, can anybody speculate on what n of z would be for if z equals 0?
Well, 1 over square root of pi e.
No, 1 over square root of 2 pi e to the 0. Okay? And I'm going to write it this way, 1 over square root of 2 pi times 1. Okay? So that's what, because that's what e to the 0 is, right? Okay? Okay, for negative 1, what is it?
Point.
It's one over square root of 2 pi e to the negative 1/2, right? Now e is what, approximately? You worked it out. 2.718281828. A lot of you used a big enough value of n to get all that, okay? So it's approximately 2.18, 2.718, okay? So that's really square root of like 2.7, approximately. And I'll just use 2.7 for right now. Okay.
Why is the exponent negative 1/2?
Because z is 1. Oh, z is negative 1, but negative 1 squared is 1, right?
Yes, 1.
Huh?
Yes.
Yeah. So if z squared is negative 1, what's your exponent?
Oh, it's over 2. Sorry.
Yeah, there's a 2 there. Yeah,
That's not z.
that's all right, that's good. Okay?
Why is that?
Now, huh? What's 13 squared?
The opposite of negative 1 squared. So negative
I'm sorry, not 13 squared. What's,
is
what two squares is 270 between whole numbers? Well, 18 squared is 324. Wait a minute. I'm squaring the wrong numbers. Okay, 15 squared is 225, right? 16 squared is 256. 17 squared is 279, right? I went to 18 instead of not 16. So this is between 1.6 and 1.7. Closer to 1.7. Okay? And it's actually, it's the reciprocal of this, right? It's the negative 1/2 power, so it's reciprocal to 1/2 power. So we get approximately 1 over square root of 2 pi times 1 over 1.7, which is approximately equal to 1 over the square root of 2 pi times 0.6. And there's some fudges in that calculation. But if you do it in your calculator, you find out it's pretty close to 0.6. Okay? This number is a little less than 1.7. It's kind of pretty close to like 1.66, which would give you a 0.6. Okay. Anyhow, or 1.625, whatever. Okay, so, okay. The point is you can calculate this. You can calculate it in your head if your mental arithmetic is up to it. And try to get your mental arithmetic up to doing that. Not instantly. I'm not going to test you on it. You got to keep using it. Keep your calculator as far away from you as possible, and don't use it unless you absolutely need to. Then use it to check your result. That reinforces your mental arithmetic. Yes?
When I put it in, I got like it's quite a bit different than that answer.
What did you get?
Well, I got .096.
Well, you probably did the 1 over square root of 2 pi.
No, I plugged in like the -2 into the equation and got
-2?
-1.
Okay. Well, let's not worry about it, but show me later what you did in your calculator so we can resolve that. We don't want to take the time right now to check the calculation. Take my word for it, and correct me if I'm wrong. You're going to get 0.6. And you're going to get the same thing here. Okay? And then if you plug in 2, you're going to get e to the -2, right?
I plugged it in for -1, and I got 0.2419.
For e to the -1/2?
Yeah. 1 over square root of 2 pi times e to the -1/2. I got 0.24.
And I have to see it in your calculator.
It's right here.
I don't have time to look at it right now. We want to do this. I mean, I have time, but I don't want to take class time to do it. But hang it on there in a minute. When I ask you to graph this, I'll look what you got, okay? And here we're going to get something like 0.13, I think. Okay?
X and Y coordinates.
Now, this tells me that you can make a pretty good graph of this normal distribution without labeling your altitudes by making a line of any length. This will be your middle. So your distribution is going to do this, okay? And then if you come out, this is for z equals 0. Then for z equals 1 and z equals 2, well, this is 60% of this, right? Do we see this?
Something.
Accept my numbers. I'm quite sure they're right, but we'll see why your calculator.
Well, he's saying that 1 over 2 pi times 0.6.
Yes.
Yeah, but
That's what I got.
E to the -1/2 is 0.6.
you probably got your parentheses wrong, or you're doing something wrong
Got
with
the
signs.
parentheses over -1 that I did.
So that's why I have to see what you're doing, and I don't want to debug that right now. I want to stay on the task here. If you calculate it correctly, get your numbers in there right, this is what you're going to get. And if it's wrong, I'll certainly admit it, okay? But I'm really sure this is right.
Really?
It is
Okay.
right. E to the -1/2 is 0.6.
Yeah,
So
See?
he's right.
yeah.
So
Yes.
we didn't need that discussion, although we needed to have that discussion after I'm off camera, right? And after we've seen the train of this and not gotten hung up on an arithmetic detail.